Hello everyone, welcome back to the class, and this is our second class of the chapter which we were dealing, that is electric charges and fields. And let us have a small recap of what all we studied in the last class before going to the further concepts. So now we in the last class we studied about what is electrostatics, what are charges, what is the process of electrification, what is the meaning of it, definition, and with the example also we studied what is electrification. And we already know from our lower classes what is conductors and insulators. We studied about grounding or earthing, and we also studied about the properties of charges, which is so very important in the exam point of view. And we have got three properties of charges, that is your additive, conserve, charges are conservative property, and quantization of charges. And also we have studied about what is a coulomb's law, and along with the definition we have learned, or we know what is the equation for the forces between two charges, and that is F is equals to K Q1 Q2 divided by R square, and K is a arbitrary proportionality constant, and K depends on which medium the charge is. Now going to know what is the value of K in vacuum. So SI system, in particular in SI system for vacuum, K is 1 divided by 4 pi epsilon naught, where epsilon naught is absolute permittivity of free space. Say in case if this epsilon naught of, if it is not for a free space, if it is for any of other medium, the value of this epsilon naught, which is given as 8.854 into 10 to the power of minus 12, will be changing if the medium is changed, and this value is only for the free space. And if it is for water or any other medium, this value will be obviously changed, and later on giving the value, that is 1 divided by 4 pi epsilon naught, the value is 9 into 10 to the power of 9 Newton meter square per coulomb square. So this is what we learned in the last class. And further going, we have got definition of coulomb. So what do you mean by a coulomb? It tells you that if there are two charges, okay, so a charge is said to be 1 coulomb when it is repelled by a force of 9 into 10 to the power of 9 Newton. So two charges will be there, and those charges will repel, or not only repel, or it may attract each other with the force of how much, 9 into 10 to the power of 9 Newton, from another similar charged but placed at a distance of 1 meter. Hope you're getting my point. So if I consider this diagram, the forces between these two charges is 9 into 10 to the power of 9 Newton. And what would be the distance of these two? It is 1 meter. Then I can say it is 1 coulomb. So 1 coulomb tells you that the charges or the forces between these two charges should be 9 into 10 to the power of 9, and the distance between these two should be 1 meter. Then you will call that to be as 1 coulomb. Hope I made it clear to you. So going back again to the previous slide, so yes, it says that 1 coulomb means what is 1 coulomb? When two charges are repelled by a force of 9 into 10 to the power of 9 Newton from another similar charge placed at a distance of 1 meter, and in which medium? In vacuum, they say. So these are all the units. You have to just know what is it. Is that clear? Next, coulomb is a big unit, they say. So if I consider this coulomb in a smaller units, I can write micro, nano coulomb also. Okay. further going to another concept, that is your vector form of Coulomb's law. So what is it? So I would represent my Coulomb's law in a vector form. So what is vector? So what is a vector? So it tells you about the magnitude as well as the direction. Is it? Vector means what? It is telling you about the magnitude as well as direction. So they are telling you give the vector representation of a Coulomb's law. So what do you mean by Coulomb's law? That is, you are finding the forces between two charges, is it? So now what we are going to do? We are going to keep the forces in which form? In vector form. That's it. So you already know the formula for force according to Coulomb's law, that is F is equals to 1 divided by 4 pi epsilon naught. K means how much? 1 divided by 4 pi epsilon naught q1 q2 divided by r square. And when you represent this in the vector form, let us go with the charges. With this diagram, you have got two charges over here, and this is your first charge, it is q1, and this is your second charge, it is q2. As this is positively charged, you can see that it is having a repulsive forces. It do not attract. Like charges never attract, but they repel each other. So now if I consider only this charge, yes, this exerts a force on this charge. This one exerts force on this charge. So both exerts force on each other. Now, if I consider F12, which is given in the first definition or first sentence, F2 means what? So, force on Q. So, always next to F, whatever the number is, 1, that is a charge which experiences certain force by another charge. So, I'm telling you, force on Q1 due to q2. So charge 1 is experiencing a force by charge q. Charge 2. Okay, now if I consider f21, so here charge q2 is experiencing a force due to q1. Hope I made it clear to you. Here q1 is experiencing certain forces by what? q2. Okay, so at that point, what will I write? F12 you'll write. Now, if I consider charge Q2 is experiencing certain forces due to what? Q1, then I'll write F is equals to 2, 1. Is this clear? Now, if I consider the vector form of Coulomb's law, what you're going to write here? The same thing what I told you, F12 is it? So then you will write K q1 q2 divided by r12 square. So what is it? So for the distance also you're going to mention which charge is experiencing forces due to which other charge. So what is this r12 and cap? You should get a cap. It is not visible. Make sure there is a cap over here. So what is this extra term given? It is telling you about the direction of the forces. Yes, so q2 is exerting forces on q1, or q1 is exerting forces on q2. Is this clear? Now, so this is the vector form of Coulomb's law. In the same way, similarly, so you got this much. If I consider similarly for F21, so you're going to write your distances to be as a 2 1 cube r 2 1. Is this clear? So now if I consider r12 cap, so what is the formula of r12 cap? So this is your direction, it tells you, which is equal to vector divided by magnitude. So vector r, vector symbol, you have got one arrow mark over there divided by magnitude. You substitute this value in this equation, you would get, as this is your magnitude, r gets multiplied to the denominator here when you substitute, and then you're getting f12 vector is equals to r q1 q2 divided by r12 cube r12, which is telling you about the vector form of Coulomb's law. Next, going to another concept, that is something called as principle of superposition. So what is this principle of superposition? See, here you have got many charges. Yes, as I told you, we understood what is the formula for forces according to Coulomb's law. So F value is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square. So if I consider the superposition, principle of superposition, it tells you about the net forces of what, of charges. Okay, so due to a system of charge, so if I consider this whole thing as a metal plate, clear? So a metal plate has got many tiny atoms, many tiny atoms. On that atom there might be a positive charge, negative charge, anything. Due to the process of electrification, an atom carries some charges, it might be positive or negative, due to the removal or adding of electrons, due to the process of what, electrification. And as I told you, these charges exert force on another charge. So what is it doing? The forces exerts for the charges exerts force on another charge, any of the charge. This may exert force on this may exert force on this, or this may exert force on this. So when I consider individual forces, I consider these two. Yes, so if I consider these two, just let us imagine all these three charges are exerting forces on Q1 according to the picture. Now what do? I'll take two charges separately. So after taking separately, firstly, if I take these two charges, the forces between these two is F12. So yes, Q1 is exerting forces by what, Q2. So it's been exerted a force due to which charge, Q2. So you can see, I can write according to the vector form of the Coulomb's law, F12. Yes, now if I consider these two, Q3 exerts force on Q1. So I'll write it as F13 according to case 2. Now if I consider the charge Q4 exerting force on Q1, I would write F14. Yes, so here you can see according to the picture, the charges, that is Q1 is being exerted by forces due to which are all the other charges, it is Q2, Q3, Q4, and algebraically you're summing all these forces and you would get a net force on a charge due to the system of charges. So the whole metal plate, if I consider, as you are going to add all the forces, you're getting the net force on a charge due to the system of charge. Hope I made it very clear to you what is the principle of superposition. Next, going to another concept. So we studied about electric charges. Now we will be studying about electric field. So what does electric field mean? So as I told you, charges exert some sort of forces, and if there is a like charges repulsive forces, unlike charges attractive forces, you would find. So in the same way, if I consider just a charge, the charge itself produces a field around it. Okay, and that field exerts a force on any other charge when it comes into the field of it. Now just understand, it is a region where charges experiences a force. Yes, if I consider this as a positive charge, it is creating one field around it. Okay, now what will happen if this negative charge come into the contact of the positive charge field? Okay, there is a field over here. Okay, if the electric or negative charges come into contact, okay, within this field, if it comes, it experiences some force. So what kind of force it will experience? As this is a positive charge, as this is a negative charge, attraction takes place between the positive and the negative charges, and this is something called as electric field. So, the concept is introduced to explain how a charge exerts a force on another without any contact between them. Yes, there is no contact between them, but then also you can see that both are being exerting forces on each other, and this is something called as electric field. Now, giving the equation or the formula for the electric field, we can say that firstly, the electric field produced at a point due to a charge Q. So, if I consider according to this picture, you have got a capital Q, it is a charge, and it is radiating or spreading out the fields around it. So now what do? I take one point charge where you can see a small q over here. I just bring that q into the field of this capital Q at the distance of r. See, r you can see, and now the distance between these two is small r. So what is the equation given for the electric field? That is, the charge capital Q is producing, that is 1 divided by 4 pi epsilon naught. Only capital Q you're considering now. Why only capital Q you're considering? Because your this charge is producing electric field, and this test charge small q doesn't come into picture, and that is not included in that. In which one? In this formula. So E is equals to 1 divided by 4 pi epsilon naught capital Q divided by R square, and R cap is nothing but it gives the direction of how the fields, electric fields, are radiated. Now, if I consider this force, what is the formula given? Forces between two charges, if I consider, so q is it? So 1 divided by 4 pi epsilon naught q divided by r square. And now understand, F is equals to q, small q, you take it aside, and if I just remove this q, small q, you can see that 1 divided by 4 pi epsilon naught q, capital Q divided by r square is nothing but your capital E, that is your electric field. So I am substituting this value in this equation, and what would you get? F is equals to Q E, your electric field, and therefore the SI unit of electric field is a Newton per coulomb. So what is the SI unit of electric field? It is Newton per coulomb, and also you can write as volt per meter. So next, going to another concept, that is electric field due to a system of charges. So didn't you study about the superposition of forces, where many atoms will be there, and that carries some charges, and due to that charges some forces are exerted on another charge, and that force is being added algebraically, I had told you. In the same way, if I consider in one metal or anywhere, you have got many charges. So you can see through this picture, that is q1, q2, and this is q3, this is q4. And due to these charges, these charges produces what? Electric field it produces. Hope I'm making you very much clear with this diagram. So it is producing electric field. So q1 is it, q1, q1 is exerting or radiating a electric field around it. And due to the many charges and the fields that it's producing, using the principle of superposition, again I can write it as E is equals to E1 plus E2 plus E3. And for E1 plus E2 plus E3 and so on, you just go substitute the formula for every single electric field. And but you have to mention it for which charge. If I consider q1 charge, it produces E1 electric field. If I consider q2 charge, it produces electric field 2. And that is why you have to write in the formula 1 E1 q1 r1 here. So here also you'll be writing for the next charge, it is E2 q2 charges. Which charge? q2 is producing electric field E2 and at a distance of r2. So this is how you're going to write the principle of superposition of what? Electric field. So next, going to another concept, that is electric field lines. So till now we were studying about electric field, so we'll be learning about electric field lines. So why do we take electric field lines? So lines we are just considering just for our convenience to understand the concept, and there is nothing to do with this field lines and all. It is just for our convenience we are taking few concepts into consideration. Now if I consider electric field lines, so you have to know what are the paths and what is the electric field lines. So it tells you, according to this one, the path along which a unit positive charge moves or tend to move in an electric field. Yes, already I told you this field exerts certain forces. And now as I told you, according to the charges, there are two types of charges. It is positive charge and a negative charge. If I consider this positive and a negative charge, the electric field lines of a positive charge is radially radiated outward. So ಹೇಗೆ radiate ಆಗಿದೆ? It is radiated outward. Now if I consider a negative charge, so the fields are inward, the fields are inward. So you may get a question telling you that you draw a field lines, and for what? For a positive charge and a negative charge. And this is how you are going to represent it. Just put a positive symbol and just draw few arrow marks radiating outward. And if I consider the negative one, it is just going inside. The electric field lines are going inside. So this was experimentally proved. So I hope I have made it very clear to you. Next, going to another concept, so which is based on these electric field lines only, and that is the properties of field lines. So what are these properties? Yes, in your examination these things also you will be getting actually in the recent the students who have passed out writing the examination have in their question paper of this year, they have got a question asking for the properties of field lines to be written for 2 marks. And so this is very much important. See, as I told you, electric field lines looks in this way. Yes, So now what are the properties of these lines are? So originates from, the first point is originates from positive charge and terminates at the negative. Yes, so it is originating from the negative, sorry, from the positive, and it is terminating, it is ending up at negative. So this is one property. Yes, so it is emitting from positive and terminating at negative. Okay, so they are always normal to the surfaces of the conductor. So normal perpendicular, it tells you. So next concept is, so next point is they never intersect. So what do they say? The field lines never intersect. If this is the line, another line won't come and intersect. They never intersect in this way, forming any sorts of junctions. No. So all are spread out and they never intersect in this way. Next, it tells you that it do not form a closed loop, and in charge free space field lines are continuous and without any breaks. So you can see that, do you find any sorts of breaks? No. So they are continuous and they do not form any sorts of loops like this. No loops, no intersections, no discontinuity. So these are the properties of field lines.